All right, good morning, everyone. So today we're going to begin a discussion, a presentation of graphs, graph algorithms. And before we talk about the graph algorithms, a little bit about the graph representations. This is a discussion that will take us 3 lectures, possibly even 4. So it's a huge topic. At one time, Queens actually had a graduate course. There was a professor named Howard Wasserman who has retired quite a while ago. I think he taught an entire course in graph algorithms. And I'm told that some of the faculty members, there was one, I don't know if he's still on the faculty or not, when he taught discrete structures, he just did graph algorithms. That was what he did the whole course. So it's a very important, important topic. So what is a graph? Okay, so graph is an example of an abstract data type. And can someone tell me what that means? What does it mean to have an abstract data type? How is that different than, let's say, data structure?
It doesn't have any return type.
Okay, well, the return type could be the abstract data type itself, but what we don't know is the implementation. All right, we don't know the implementation. So to take a specific example of an abstract data type is a graph. So what is a graph? A graph has vertices and it has edges. Okay, vertices are also called nodes and edges are also called arcs or relations. Avoid the word connection because connection means something else in the context of graphs. Okay, so what we don't know from the abstract data type is how is this being represented? And on the next slides, we'll talk about different ways we can represent that. Maybe I'll ask you first. We talked about this briefly in our lecture on data structures at the beginning of the semester, but what does the abstract data type do? It will enable you to add a vertex. It will enable you to add an edge. It will enable you to ask questions about which vertices are, let's say, connected to which other vertices. But it doesn't tell you how that's being done. It doesn't tell you how the edges are being stored. It doesn't tell you how those questions are being answered. So that's what we mean by an abstract data type. Now, something else before we move forward is until now, when we spoke about, let's say an algorithm was O of n, or n log n, or n squared, what did n mean? So let's say when you say merge sort is n log n, what does that n stand for?
Number of elements.
The number of elements in the array, right, or in the structure. Okay, if we say that a graph algorithm is O of n, or O of n squared, or O of n log n, what does n mean?
Assume vertices.
Well, it's reasonable to assume that, but it could also refer
Number
to
of
edges.
edges.
It could also refer to edges, so it's ambiguous. It's ambiguous. Okay, so what we are going to try to do, and I can promise you I'm going to fail, but what we're going to try to do is we're going to try to say O of V, or O of E, or O of V log E, or O of E log V. We're going to try to use V and E, okay, and try not to use M and N, but I'm sure that sometime in the next few lectures, when we talk about graph, I will say it's N squared, or N log N. I'll make that mistake, but again, it's misleading because we don't know what the n refers to. And in one book, n may be vertices, in another book, n may be vertices, and n is edges. So we have to really be careful. All right. So what does in our graph? So the vertices represent something, and the edges represent relationships between them. So for those of you who took discrete structures or discrete math using that big Rosen book, there's something interesting that the Rosen book did. It has a chapter 2, and in chapter 2, it talks about functions, it talks about sets, it talks about all the math that you need to know really for the rest of the discrete structures. It talks about cardinality, it talks about matrices, and there's one piece that gets left over. There's an entire chapter, not till chapter 9, about relations. And part of the reason that it's separated out, normally I think of functions and relations and sets as all being related. It puts the relations later because the relation sets the stage for a graph. Because what is an edge? An edge is a relationship. It's saying you have the set of vertices and the set of vertices. So think of the Cartesian product, all possible edges between them, all possible relations between them. And it says which of them, are true and which of them don't exist. So what do these edges represent in real life? And they can be used in a lot of different ways. So this is interesting. So it could represent that two things are contiguous. Contiguous means you can, go from here to there. So for example, if I have, a street here and a street there, and I can go from one street to the other, I can walk down the block and get to the other street. We might put an edge to say that they are physically adjacent to each other, right? So that's mean by physical. It could be a chronological thing. So if you go to the department website, and I actually have it on one of my slides here, although it's outdated because they changed the requirements, they have a flow chart of the courses you need to take, right? So first you need to take, some introductory course, and then you're going to take another introductory course, and then you're going to take data structures, and in the meantime, you have to take some math courses, and then you can take 323, right? So they have arrows. It's a graph. It's a directed graph, and that's a chronological graph, right? It's saying you got to take this before you can do that, right? So you can use a graph to represent that. You could have a causal, okay? What do I mean by causal? So if you take data structures, it doesn't mean you then automatically take analysis of algorithms, right? You may decide, I don't want to take analysis of algorithms. I don't want to major in computer science anymore. I hated data structures, right? So it doesn't mean that A makes B happen. It means, A may come before B. So we could have a causal relationship, which means that yes, one thing does happen, right? So if you, I don't know, you cut the cord on your refrigerator, so an outcome of that is that the refrigerator is going to stop working, and the food that you have in your refrigerator is going to get spoiled, right? So that's an example of a causal relationship. You can have biological, that's a kind of causal, it's not exactly cause, but it's a biological relationship, right? So an animal gave birth to another animal. So there is a biological relationship between them. And you can have emotional relationships, right? Something is, one person loves another. All right. Here's a question. It comes up later on the slides, but this is a good time to talk about it. So are these relationships symmetric? So first of all, what does that mean? What does the word symmetric mean in the context of relationship?
All sides are the same.
Well, what?
Like both sides are the same, left,
So
right.
it goes the same forward and backward. In other words, if we have an edge UV, then we also have an edge VU, right? The relationship works both ways. So is that true? Well, for physical, if A is next to B, then probably B is next to A. In chronological, it's the opposite. It's not true, right? If A has to come before B, then it's probably not true that B has to come before A. Causal, also probably one direction, right? A causes B doesn't mean that B causes A. And if an animal gave birth to something, it's unlikely that the baby animal gave birth to the mommy animal, right? What about love? What about emotional? Is that symmetric?
Oh,
So the world would probably be a better place if it was, but unfortunately, it doesn't always work like that. Okay. So that's one of the things we have to understand about relationships. That's one of the things we have to understand about a graph is it symmetric or is it not? If some of the edges are bidirectional and other ones are not, we don't count that as symmetric. Symmetric means it's got to always be true. All right, so that's this directed and undirected, right? So again, as a matter of course, just because I have an edge UV, or we could write with braces or with brackets rather, or with parentheses, it's generally assumed to be directed unless we hear otherwise. So if someone tells us the graph is undirected, or if someone tells us the graph is symmetric, then it's symmetric. But if we don't know that, we can't assume that, right? If it is symmetric, then if you want, you could use curly braces, because what do curly braces represent in math and Python?
Set.
It represents a set. And what do we know about sets? a lot of things about sets, but one of them is that the order doesn't matter, right? The order of a set doesn't matter. The order of a tuple does matter. The order of a list does matter, but the order of a set does not. So therefore, sometimes people will choose to use, if it's undirected, they'll represent a edge with a curly brace to indicate that the order doesn't matter. All right. So again, symmetric means that all the edges are, the order doesn't matter. UV is the same as VU. All right. Another, a lot of terminology. Okay. One of the problems with the graphs is that so many words in that we use in English have specific meanings in graph theory, and it becomes very difficult to talk about a graph without meaning something that you didn't necessarily intend. For example, if I want to say a graph is a regular graph, okay, what does that mean to you? It means, well, maybe it's not a special graph, but in graph theory, it means something specific. So if you look at this last bullet point, the last bullet point says that a regular graph is a graph where every vertex has the same degree. It has the same number of neighbors. And we even have some notations for that. For example, the cycle graph, C of n is the cycle graph. It means that every vertex has a degree of 2. It's got one going this way and one going that way. And if you put them all together, you get a big cycle, right? Anyone know what this Kn stands for?
Total number of edges.
No. K stands for complete. Now, you probably didn't know that complete begins with a K. It doesn't. Why do they use K for complete? Because they use C for cycle. So they needed to come up with something else. All right. So what is a complete graph? A complete graph is a graph where every vertex is adjacent to every other vertex. How many edges does it have? N times n minus 1 divided by 2. Why? Because every vertex, for the n vertices, you multiply by each other vertex is n minus 1. We divide by 2 because it's generally symmetric. So a complete graph is generally a symmetric graph. So a edge, B edge from A to B is the same as an edge from B to A. All right. So let's just back up a little bit here. So every vertex has a degree, which is the number of neighbors. If it's a directed graph, then we need to differentiate between the edges that are going out. We use that plus sign to indicate edges that are going out, and a little superscript minus sign to indicate the edges that are coming in. We call that an in degree. If it's a symmetric graph, the out degree and the in degree of the vertices are the same. If you add up all the edges in a directed graph, it comes out to be E, all the degrees. If you add it up in an undirected graph, it's 2E because each vertex contributes to a degree twice, right? Coming in and going out, all right? So it's a little counterintuitive there, right? So here you see a picture of a directed graph and an undirected graph. Notice that in the undirected graph, so an edge between 4 and 5 means I can go from 4 to 5 and I can go from 5 to 4. That's not true over here, right? So I can go from 3 to 2. I can't go directly from 2 to 3. But sometimes in a directed graph, we do have an edge that goes both ways, or 2 edges, right? One going this way and one going that way. So that is possible in a directed graph. All right. So how do we represent the graph? So remember when we talked about the abstract data type, I told you that it doesn't tell us how it's implemented. So now we're talking about how it's implemented, right? Behind the scenes, right? If we turn our data type into a data structure, we need to talk about implementation. So we have 4 ways to implement it. Okay, there could be more, but these are the ones we're going to discuss. They are adjacency matrix, adjacency table, edge sets, and then like a hash map. All right. So what is the adjacency matrix? This is probably the most popular. It's a matrix. Every entry in the matrix is either a 1 or a 0. 1 means that I is adjacent to J. Vertex I is adjacent to vertex J. And if it's 0, it means vertex I is not adjacent to vertex J. So all the entries are 1s or 0s. Okay, and then it's going to be symmetric if the matrix is symmetric, right? If Aij is the same as Aj, fine. Generally speaking, when we talk about graphs, we require them to be loop-free. What does loop-free mean? So loop doesn't mean like a for loop or a while loop. What does it mean? It means no edge from a vertex to itself. All right. So you can't have an edge from I to I. You can't have from vertex 2 to vertex 2. You can have a cycle. Okay. So imagine for a moment that we took away the arrows here, right? So this would be a cycle, but it's still loop free because nothing is going directly to itself. So in terms of the adjacency matrix, the diagonal will be 0 because the diagonal is position 1, 1, position 2, 2, position 3, 3, position 4, 4. So those all need to be 0 because it's a loop-free graph.
Professor, what
Yes.
does the A bracket IJ mean? Is that the edge between
This?
N and J?
This,
Yeah.
that stands for it's A is the adjacency matrix, it's saying row I, position J of the matrix, means that vertex I, let's say it's 1. So it means that vertex I is adjacent to vertex J. There is an edge. So if you look at this picture here,
Mhm.
okay, look at that picture there. So here we have an adjacency matrix. Okay, so how do we read this? All right, so first of all, it's a little confusing because the vertices here are numbered 1 through 4, but the adjacency matrix uses a Python or Java notation, right? It's 0 through 3. So this is saying 1 to 1 is not, right? There's nothing, right, from a vertex to itself. This is saying from vertex 0 to vertex 1, there is an edge. So again,
Oh,
you have
okay,
to
I see.
subtract off 1 here, right?
Is the adjacency related to the directed or not directed?
Adjacency matrix could be used for both. So if it's a directed graph, then just because Aij is something doesn't mean that Aji is the same. If it's undirected, then the graph is symmetric. And
Okay.
then Aij will always be equal to Aji. So that's depends on whether it's undirected, whether it's symmetric or not.
Got it.
Okay. All right, so our second representation is what many books call an adjacency list. I prefer not calling it adjacency list. I prefer calling it an adjacency table. Okay, why do I like to call it a table? Because it's really a bunch of lists, right? We have a list for vertex 1, right? It says that 1 is adjacent to 2, and it's adjacent to 3, and that's it, right? That's the end of the list. Okay, 2 is adjacent to nothing. 3 is adjacent to 2 and 4, and that's it. And 4 is adjacent to 3, and that's it. So I think, this is a list, and this is a list, and this is a list, and this is a list. But I think calling it an adjacency list is a misnomer. So again, I have to be honest with you, probably more books call it an adjacency list than call it an adjacency table. And I will probably here and there call it an adjacency list myself, but I actually prefer the term adjacency table. It's sort of like, a little bit like a hash table, with chaining, right? Like a hash table with chaining, right? It's all the neighbors of something go into one chain. Right, our third representation is the edge set. And in the edge sets, we don't really keep track of vertices. We just keep track of the edges. Everyone see that? So we have edge 1, 2, edge 1, 3, edge 3, 2, edge 3, 4, edge 4, 3. So the space complexity is going to be order of E because it's just dependent on the edges. We don't keep track, we don't have a separate list somewhere of 1, 2, 3, and 4. We just keep track of the edges. So if something doesn't have any edges, it's it's not important enough that we're going to include it. Okay. And then we have one more representation is the hash map. Okay, so in a hash map, we use as a key an edge, right? So we'll put 1, 2 as a key, and we'll store, the value true or 1 or something to indicate that it's there. Now, what's the advantage to a hash map? Graph representation. So what's the advantage to a hash map in general?
Lookup time.
Lookup time. So if our primary use of the data structure is to find out whether, an edge exists or not, right? If it exists or not. So then a hash map is very good for that. Okay, it's not so good for other things. If I want to know all the neighbors of a vertex, but it's very good for just, telling us, does the edge exist or not? So again, to summarize, we have 4 representations that we discussed: adjacency matrix, adjacency table, edge set, and a hash map, which is really like an edge map. It's a hash map of the edges. The 2 that we will use in this course are, we'll often use the adjacency matrix and the adjacency table, not so much the other 2. All right, so here is a little bit of a summary. Okay, so depending on what you need to do, they have different pros and cons. Okay, so I sort of summarize here. For example, if I want to find the neighbors of a vertex, so if I have an adjacency matrix, what do I need to do? I need to look at the entire row to find out its neighbors. If I have an adjacency table, I need to look at the chain. I need to look at that linked list. If it's an edge set, I need to look at all the edges and figure out which ones have my vertex in them. And if it's a map, again, I need to look at all the things that are in there to find out, okay? But other things are, the map is better, right? Here we have O of 1 for the map. So depending on what operations you need to do a lot of, that may determine what kind of representation to use. Okay, so we can make this a little bit more complicated, and we can say, we don't just care whether there is an edge or there isn't an edge, but we want to weight the edge. Okay, we want to weight the edge, which means, some edges are worth more than others. For example, let's say I have, 2 neighbors, but one neighbor lives 100 feet this way and another neighbor lives 50 feet the other way, right? So the cost of going from one neighbor to that neighbor is not the same as the cost of going to the other neighbor. So we need to keep track of these costs. Generally, the weights are costs. Sometimes they could represent value. For example, one of the algorithms we're going to discuss, not today, is something called the max flow. It has to do with, back when it was introduced, it had to do with things like water, right? So we want to know how much water can we get from, let's say, the water pump, the water tower in town to a destination. So you look at the sewer, or not the sewers, the pipes, right? How big are the pipes, the different pipes that go, and that'll help us determine how much water we can get to a certain place within a certain amount of time. Let's say the fire department may be very interested in a question like that. All right, but so in that case, the edges are capacities, and that's a good thing. Or, to take a more modern example, you have a network traffic, right? So you have a bunch of channels, wires or fiber optic cable, right? Each thing has a capacity, right? How much you can transmit over that in a per second, right? So you want to know, so the weights are actually good. But in most problems, the weights on the edges are bad, right? They represent a cost, it's something bad. Right, so here's an example of weighted graph. So we don't just have an arrow between 2 things, but we have a cost or a number associated with it. It could be a good number or a bad number. So how do we represent that? Okay, so if we want to use an adjacency matrix kind of idea, then we can just have a cost matrix. Okay, so a cost matrix means instead of storing a 1 or a 0, I store a cost. Okay, if I use an adjacency table, I have a linked list. So instead of just storing the neighbor, I also store the cost of going from A to 12. I store the cost of going from A to D. All right, let's go back to the cost matrix, or I guess it's, yeah. What happens if the edge doesn't exist? So I am storing what cost should I store if I don't have an edge from, let's say, 1 to 2?
Infinity.
All right, so it says here the cost is infinity. Is that what you saw? Or you just know that?
I remember.
You remember that. Okay, so it's not that simple, okay? I prefer that you use infinity. So what you remember is, I like what you remember, but I will be honest with you, many books, and even more so than the books, are the algorithms that are out there, they use 0. Okay, they use 0 to indicate that the edge isn't there. Now that's a little bit confusing because sometimes you could have an actual cost of 0. Okay, the cost of infinity is actually better because it's saying you can't do it no matter how much you want to spend, right? You want to spend $1 million, you want to go 1,000,000 miles, you still can't do it. You can't take that route. It doesn't exist. So infinity is really a better way of doing it, but many books. So if you go to the Geeks for Geeks site, so at some point we'll have a graph algorithms assignment, and you may take code from there like we've been doing. So you got to watch out, okay? Their code probably is using a 0, and you'll need to, so their code isn't wrong. It just, you have to look at the code. They will do a check. They'll say if it's a 0, then they treat it, or they say if it's greater than 0, then we'll treat it like the edge exists. So they have code that accounts for that, but just watch out for that. So that's a common discrepancy in terms of the assumption. All right, so that's a little bit about representing graphs. Now we talk about some of the problems that we have, graph theory problems. And these are problems that happen in real life, all right? So we have different kinds of problems, okay? We have very efficient solutions, okay? So when we say very efficient, we mean linear time and the number of vertices and edges. For example, we can determine if a graph has a cycle very efficiently, right? Can you go from one vertex, around and come back, all right? Not hitting all the vertices, but just somewhere in there, there's a cycle. We have other problems that are a little bit more difficult. For example, these are all problems we're going to talk about. Minimum spanning tree, the single source shortest path, all pair shortest path. For example, these you can do like this you can do in n squared, this you can do in n cubed, this one you can do in also v squared. If you're really good, you can do in like e log v, okay? And then we have other graph algorithms that are intractable, okay? Now, intractable does not mean unsolvable. It's not like the halting problem, okay? We can solve it, but it means it's more than polynomial time, okay? So think exponential time, factorial time, n to the n, things like that. That's what you mean by intractable. So many important problems in computer science are in this last category. I just mentioned 2 here, traveling salesman problem and the graph culling problem, right? Well, we have a whole lecture on NP completeness, and then we carry that over into approximation algorithms. So there are many graph algorithm problems that are difficult, okay? Meaning so difficult that if we can solve them, we can probably solve all NP complete problems, and we can get $1 million prize from the Clay Institute. All right, so what we're going to do today and for the next 2 lectures, we're going to talk about different graph algorithms. And a good place to start is what we call a graph traversal. Okay, so what is a graph traversal? Graph traversal means we want to visit all the vertices of a graph. So how do we do that? And we have 2 main strategies for that. One is called a depth first search, and the other is called a breadth first search. All right, what are those? So in a depth first search, you visit a vertex, you visit another vertex, and then from that vertex, you see where you can go. And from that vertex, you see where you can go. So you try to go as far as you can. It's sort of like in a maze, right? In a maze, you try to go as far as you can. When you get stuck, what do? You back up a little bit and you see where else I can go. When you get stuck, come back and you see where you can go. So that's called the depth first search. We try to go as deep as possible. And when we get stuck, we can't go any further, we back up a little bit, and then we try something else. And eventually we work our way back to the beginning. Okay, breadth first search works differently. In a breadth first search, you visit a vertex, and then you visit all of its children. And then you keep track of what those children were, and then you visit each of its children. And then you keep track of what those children were, and you visit each of their children, and so on and so forth. So I have an interesting question for you. And that is, does anyone know what a web crawler is? Some of you may have even written a web crawler. In my 355 course, so when we do it in PHP, one of my lectures that we have a code for a web crawler. So it's different than web scraping, right? Everyone know what web scraping is, right? Web scraping is I identify, a page on the internet that has some information I want, and I write code to extract that information from the page, right? But what is web crawling? Anyone know what web crawling is? So web crawler is a program, usually runs like in the background. And what it does is it just visits a lot of websites. And it takes information from them. It may just look at the header of the website. It may look at every word on the website, but it visits websites. It keeps track of the websites that it visited. And then it stores that information in some kind of database, right? So Google, and Yahoo, anything that has a search engine has to have some kind of web crawler that crawls the web and does this. So here's my question for you. You can think of each web page as a node. And then web pages are connected to each other. For example, if one page has an href, so those in 355 know what that is, or if you know web general, right? So you have anchor tags and they point to other pages and other resources, right? So you can say they're connected to each other, right? If this page mentions another page, it's got an href to another page, so there's like an edge between them. So you can think of the web pages of the world as a graph. And it's a directed graph because if page A points to page B doesn't mean that page B points to page A. So with that, if you're writing a crawler, would you use a breadth first search or depth first search, or maybe none of the above, but of these two choices?
Breadth first search.
Okay, why do you say that?
Because it's not going back, it's only going forward.
Well, a depth first search, maybe I didn't explain it clearly before. When you go back, you're not going back to try to do something again. You're going back to where you came from so that you can go forward from there. It's sort of like in a maze. So in a maze, when I go back, I'm going back so I know where else I can go.
I think that first, because
But I still agree with you about the breadth first, but I just want to clarify the reason. Go ahead. What were you saying?
I thought it should be that first, because like for search engine, you don't need the sub page, you only need the home page,
Yeah, but what you're trying to do is you're trying to see, you don't want to get stuck on one particular thing. Okay. So let's say you go visit, a page from there. And then you're gonna get stuck in whatever pages it has, but you tend to lose, the breadth of the choices. So generally speaking, I mean, there's no one right answer here, but generally speaking, you probably want to do a breadth first search, which is okay. So where is this thing pointing? Let's try to scout that out, and then we'll go back and try to get more detail. Here's something that happens. So in general, web pages, not like Wikipedia. Well, even Wikipedia is true. So generally, websites like to point to themselves. Okay, not to the same page, but they like to point you to other pages on the site. See, if you're a business, the last thing a business wants to do is send their traffic somewhere else, right? If you're Amazon, you're not going to send someone, you're not going to send them to Walmart. You're not going to send them to, I don't know, another big vendor, all right, Costco or to Target, right? You want them to go to another Amazon page. You want them to buy something from Amazon, unless it's a authorized third-party seller and they make some money from that. They get commission, so then maybe it's worthwhile, right? So a lot of websites, they have a lot of links, but there are links to other pages within that. So if you do some crawling, you'll discover that tend to refer back to themselves a lot. Okay, that's just in terms of a practical application. So here we have a breadth first search. All right, take a look at the data structure that breadth first search typically uses. It's a queue, right? How is it using a queue? Because when it visits something and then it visits its children, it puts all the children on the queue, and then it goes back in first come, first serve order in FIFO, first in, first out order, and it visits all the things that are on that queue. I'm sorry, it visits all the children. So look what it's doing in this while loop. It takes something from the queue and it pops it, right? It prints it out, fine, and then it visits the neighbors. It says, okay, by the way, what this is doing, what this line means is it's basically saying the neighbors of S in the graph. So it's saying if you're in the list of neighbors of S and you haven't been visited already, then we're going to add you to the queue, and then we're going to pop you from the queue and we'll visit your neighbors as well. Right? So that's the basic strategy for BFS. Can anyone tell me the time complexity of this? And remember, when we talk about time complexity of graph algorithms, we don't say O of n anymore. We try to say O of v, or O of e, or O of v times e, or O of v plus e.
O of v.
So let's try to figure it out. So this line here, if you're not familiar with Python, that'll probably look a little funny. This is initializing an array. Okay, so how big is the array? It's the size of the graph. In other words, the width of the graph. So that's basically v. So this line here, even though it looks like it's one line, is actually an O of v line. Okay, what about these lines here? These three lines here, how much do they take? So we need to initialize a list. That's just one
What is
operation.
S again?
S is a vertex, okay? In this case over here, it's the starting vertex. In the loop, it's the next thing from the queue, right? But here it's the starting point. It's a vertex. Okay, so we're initializing an empty list, an empty queue. We're inserting something on the queue, that's one operation, and we're marking it as visited, that's one operation. Okay, then we have a list. Then we have a loop, a while loop. So it's saying as long as the queue is empty. So how long is this queue going to take? And the answer is it's going to depend on E. Why is it going to depend on E? Because it's got to go through every single vertex once. Every vertex gets added to the queue once and it gets removed from the queue once. Okay, so it's going to take E. So the total time is O of v plus E. O of v plus E. Now, strictly speaking, I should be putting those vertical lines for size around the V and the E, but we usually just omit them because it's easier to just do it without them. All right. Here is, we should have depth first search coming up here. Here's our depth first search. Notice that depth first search is usually implemented recursively. It doesn't have to be recursive, but it's usually implemented recursively. So in this case, V is our starting point. We mark it as true. And for each vertex, we see if it hasn't been visited already. So I is the iterating over the vertices, the neighbors. If it hasn't been visited, then we visit it recursively, and then we come back to the other neighbors. So that's where it differs from breadth first search. We visit it and all of its family before we come back to the other children here. So imagine a family where the grandparents, instead of visiting each of their children and then visit the grandchildren, they visit the one child and all of the child's children and grandchildren, and then they come back and they visit the next child and all of that child's children and grandchildren. Is that fair? I don't know. Sometimes it's more convenient because maybe that parent lives closer to its children. But in any case, those are two different models, right? They're two different models about how to do this. What's the time complexity? So this time complexity is also the same O of v plus E, because every vertex needs to be visited. So it's got to be O of v, but we also have to go through every edge. We have to, for each vertex, we're always considering all the neighbors and deciding if we have visited it or not. All right, so we got a lot of graph algorithms to do. We will not do all of them today, but there are a lot of things to do here. So our next algorithm up is called transitive closure. We mentioned it briefly last class, but as I said then, we would come back to it because until we started graphs, didn't really make so much sense. So anyone know what that is? So the key word here in transitive closure is connectivity. Connectivity means, is A connected to B? Now, what's the difference between, I'm going to put two words in the chat. I want you to tell me the difference between them. So we have adjacent, and connected. Or you could say adjacency versus connectivity. What's the difference between those two words? And by the way, if you go to a thesaurus and you look up connected, you'll probably find adjacent. And if you look up adjacent, you'll probably find connected. But they're not the same thing. Not in graph theory, at least.
Adjacent means two vertices are neighboring vertices, but they're not necessarily connected.
No, it's the other way
There's not
around.
an
It's the other way around. Okay, so I agree with the first part of your statement, right? When you have two vertices and they are adjacent, that means they're neighbors. All right, but they are also connected. Okay, so once you have an edge, your neighbors, you are automatically connected, right? But it's possible to be connected, as the Cheng says, but not directly adjacent. Okay, what does that mean? It means I can go from A to B to C to D, and therefore A to D, A and D are connected, but they're not adjacent to each other because I have to go from A to B and B to C and C to D. Understand? So connected means, in the language of graph theory, means there's a path. There is a way to go from, I to J. Okay. Adjacent means there is an edge. Okay, everyone see the difference? So adjacent, there is an edge. Connected, there is a path. Okay, so that's important. So the adjacency matrix, the adjacency table, the edge set, the edge map, they all tell you about edges. They don't tell you about connectivity. For connectivity, we need to figure that out. We need an algorithm. So what algorithm we're going to use? So on the previous slide, I mentioned three different algorithms we can use for that. So we're going to look at those. All right. The first one is Warshall's algorithm. Do I have? I do have it here. Okay, so we had it in last lecture slide, and we have it again here. All right. So what it does is take a look at this code here. Okay, so first of all, it initializes this matrix, and it says initially I and J will be connected if there is an edge, right? So if there's an edge, they are also connected. But it does more than that, right? So in the main code, in the main loop, which is really 3 nested loops, it says if I don't have a path yet, but I can go from I to K and I can go from K to J, then I do have a path from I to J. Now, the truth is, if I omitted this code, this first piece here, it would still work, right? It's still true that if I can go from I to K and K to J, then I can go from I to J, even if this wasn't true already. Or it was true already. It's just I don't need to update it if it's already one. So that's why we have this extra if here. But we could remove this piece of the if. Okay, so this is very similar to Floyd's algorithm, and we'll come back to Floyd's algorithm too. Notice it's 3 nested loops, and also notice that the variable that iterates over the intermediate vertex, this K, is always on the outside. So I believe I have a review question about that. So if I come back here, let's just summarize. It's similar to Floyd's algorithm. We have to look at Floyd's algorithm again. It uses dynamic programming. How is it dynamic programming? Well, it's bottom up, right? Because it starts with the small cases, 1 edge, works its way up for 2 edges, intermediate, 3 intermediate edges, 4 intermediate edges. So it's incremental. That's the dynamic programming. It uses an adjacency matrix representation. Everyone see that? So here's your adjacency matrix, right? So that's your starting point for this algorithm. It takes O of V cubed time because you got a loop inside a loop inside a loop. So that's the V cubed. And we talked about it a little bit in the lecture on dynamic program. All right, I probably should put those 2 bullet points together, but okay. All right, so that's one approach. Now here is a very interesting approach. All right. And that is that if I take my adjacency matrix and I look at it by itself, what does that tell me? It tells me, do I have an edge of length 1? Well, every edge is length 1, but it's also telling me if there's a path of length 1, because an edge is a path of length 1. Now, here's something interesting. If I take a matrix, any matrix, to the 0th power, what do I get? Anyone learn that in linear algebra or discrete structures, discrete math? Take a matrix and raise it to the 0th power. So here's a question. What happens if I take a scalar and I take x to the 0th power? What do I get? I get 1. Unless x is 0, then it's undefined, but generally I get 1. Okay, so now if I take a matrix A and I raise it to the 0th power, what do I get? Not filled with ones. There are some ones there, but a specific portion are ones.
Identity matrix,
Again, identity matrix. And what is an identity matrix?
diagonally, it's
Diagonal, right? So position 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, right? Here is something very interesting. What does that mean? It's saying, if we think a bit in the context of transitive closure, of connectivity, it's saying there's a path of length 0 between every vertex and itself. There's no edge from a vertex to itself, but there's a path of length 0 because I don't have to go anywhere. So that's what this is saying is, okay? So A to the 0 is the identity matrix. All vertices are connected to themselves by a path of length 0. A to the 1 is a path of length 1. Now, here's where it starts to get interesting and surprising, I would say. If I take my adjacency matrix and I square it, I do A to the 2, then what happens? It will tell me there'll be a number there if there is a path of length 2. So, okay, and there'll be a 0 there if there's no path of length 2. If there's 2 paths of length 2, and that's possible, I could go 1, 2, 3, or 1, 4, 3, or 1, 5, 3, right? So I have multiple paths of length 2, that number will be reflected there as well. If I take A to the cubed, it will tell me how many paths of length 3 I have between 2 vertices. So it's a pretty cool, I wouldn't say it's obvious. I mean, once you try it, you see that it works. But we can use matrix exponentiation to help us figure this out. All right, so how do we use that? So what we do is we use the Boolean sum. I take A to the 0 plus A to the 1 plus A to the 2, and so on and so forth, up to A to the n minus 1. And what does a Boolean sum mean? So in Boolean math, in regular math, what does 1 plus 1 mean? You know that joke people used to do when you were a kid, right? You would ask someone, what's 1 plus 1? They would say 2, and you say, no, it's 11, right? Because if you concatenate them. Okay, so in Boolean, so in regular math, 1 plus 1 is 2. What about in Boolean? 1 plus 1 is what?
1.
What? It's 1, because it's like saying 1 or 1. So 1 or 1 is 1. Right, so again, it all depends on what you mean by plus. Is it concatenation? Is it decimal addition? Is it Boolean addition? So in Boolean sum, we're saying, look at the position ij in each of these matrices, and if any of them are 1, then it's a 1, right? Because that means there's a path, maybe a path of length 0, a path of length 1, a path of length 2, a path of length 3. Right, and so on. Why do I stop here? Why am I not going to A to the n plus 1, A to the n plus 2? Why am I stopping at n minus 1?
Because that's the maximum length.
That's a maximum length, correct. Why? Because once I have n vertices in my path, or n intermediate vertices, I'm repeating stuff. So why should I repeat a vertex twice? It doesn't make sense, right? If I go to vertex 2 and then I come back to 2, why didn't I need to go all around in the first place? So I shouldn't have to go from 2 to 5, I shouldn't have to go to 2 twice. All right. So that's a second way of computing the transitive closure. So the first way is using this dynamic programming algorithm called Warshall's algorithm. Second one is using matrix multiplication. And here you actually see it, right? So take a look at this picture here. This is our adjacency matrix, multiplying it by the same adjacency matrix, and I get this. This means that there is a path of length 2 between vertex 3 and vertex 1, right? Because I go from 3 to 4, and I go from 4 to 1. So you can see that there is an edge. All right. All right. So how long does this take? Well, let's go back and look at what we're trying to do here. So how long does it take to compute A times A? If A is an n by n matrix, how long does it take to compute that? So you just submitted an assignment. It hasn't been graded yet. You just submitted an assignment on matrix multiplication. So how long does it take, not using Strawson or anything fancy, just to take a matrix, an n by n matrix, and multiply it by an n by n matrix?
N squared.
N squared, not n squared,
Q.
n cubed, right? So that's a classic cubic time algorithm. Strawson gets it down to like n to the 2.8 approximately. All right. So how long does this take? Well, on the surface, it looks like it could take a lot because I'm doing A times A n minus 1 times. So that could take as much as a to the n to the 4th. And then I have n of these in the summation. So that could be n to the 5th, but I don't, that's like a silly way of doing it. You know why? Because if I compute a to the n minus 2, then I just need to multiply a one more time to get a to the n minus 1. Let me say that differently, right? So let's say I have a squared. I just multiply that by a to get a cubed. So I don't need to start from scratch. So really that should be n to the 4th, right? It should be n to the 4th or v to the 4th, right? If v is the number of vertices. But we can use the exponentiation, right? Remember where I use like a binary approach, right? So if I want to get x to the n, I can do that in log of n operations. So if I need to do v to the n, I can do that in log time. And then I could also try to use Strawson's algorithm. So I can get some kind of improvement there, right? Our third approach for transitive closure, an interesting approach, is we use DFS or BFS. How do we do that? Well, we run one of those, it doesn't really matter which one, and we keep track. Okay, we keep track of where we were able to get to. So we run DFS with vertex 1, and we see which vertices were we able to reach, and we update the matrix accordingly. Okay, then we do the same thing starting from vertex 2. We see which vertices we were able to reach using the depth first search or the breadth first search, fill that in into the transitive closure matrix, and we do that. All right. So that's another way of doing it. So who remembers how long it took to do DFS?
V plus E.
V plus E, assuming we have an adjacency table. If we're using the adjacency list, it was a V squared. I'm sorry, with the adjacency matrix, it's V squared, but yes, the adjacency list. See, I made the mistake myself. I called it adjacency list. I really should be calling it a table, but that's what the world calls it. They call it an adjacency list. So now I need to do that for each vertex. So that's where this extra V comes from. What happened to the V? If I multiply V by V plus E, so I have the VE, where did the V squared go? Why isn't it V squared plus VE? Anyone know the answer to that? So when we're doing asymptotic notation, big O, and I have two things, like I have X squared and I have X. Which one do I really care about? Right? If I
What was
say,
the question again?
okay, here, look, look in the chat for a second. So let's say I have O of X squared plus 5X plus 7, right? So what is that really? What order of magnitude is that?
X squared.
That's an x squared, right? So which of these is the bigger one? V or E, the size?
E.
E is usually much bigger, right? Because I have, for each vertex, I have many other vertices that it's adjacent to, right? So VE could be closer to V squared. So therefore, when I multiply V by the V plus E, right, it's the E that's dominating. So generally, we don't even necessarily say O of V plus E. Okay, sometimes we'll just say, instead of V plus E, we'll just say O of E because the E is typically bigger. If it's a tree, then there are actually more vertices than there are edges. Okay, if it's a disconnected graph, there are more vertices than there are edges. But generally speaking, there are many, each vertex has many neighbors, and therefore E is a larger number, not a smaller number than V, right? So we're going to go back to DFS now. Remember, we had DFS on a previous slide. And we're going to go back to it. So can someone tell me what have I changed here? What have I changed in this algorithm that we didn't have before? I'll give you a hint. I color coded it.
The discovering and finishing of the vertex.
Okay, I have a discovery time and a finishing time. So what are those? So as you can see, it looks like I have some kind of array that keeps track of the discovery time for each vertex. And I have another array that keeps track of the finish time for each vertex. And what is the time? So the time is not the time on the clock. It's not even like the time.time in Python. It's just a counter. So every time we discover or finish a vertex, we increase the time by 1. So it's not a real time. It's not in seconds or microseconds or anything like that, but it's just a counter. Okay, what is the purpose of it? Because there's certain things we can learn about the shape of the graph and the relationship between some vertices and other vertices based on when something was discovered compared to when it was finished or another vertex was discovered and finished. So those numbers are useful to us, right? So in order to do what we're going to do in the next few slides, we need to have this enhanced or modified version of the DFS. Okay, so let's just look at this picture here, then we'll come back to the definition. So as you can see in this picture, here we have a graph and we have edges in the graph, and each of the edges is a color. Okay, so again, I don't know, I never know how this looks on your end, but on my end, we have one that's like a navy blue. One color is a navy blue. Another color is like a lighter blue, more of a sky blue. We have a green and we have a red. So each of those colors represents a different kind of graph or a different kind of edge. All right, now, what do those edges mean? So I have a formal definition on the previous page, but I'm going to try to explain it to you in the context of the picture, right? The dark blue or black edges, the dark ones, those are the ones in the actual DFS tree. So what do I mean by that? It means if I started my DFS from 1, so what am I going to do? I'm going to look at 2, I'm going to look at 3, I'm going to look at 4. 4, I'm going to try to see where it goes. It goes back to 2. So that's not a DFS, that's not a DFS edge. So anything where I find the vertex originally from the DFS is a DFS tree edge. Okay, same thing over here. I'm going to go from 1 to 5, 5 to 6, 6 to 7, 6 to 8. All right, those are all tree edges. I have a back edge. What is a back edge? A back edge is an edge from something to something else that I had already found before. Does everyone see that? Okay, how did I find 2 originally? Where was I coming from?
2 to 3 to 4.
How did I originally find the vertex 2?
Oh,
From
1
1.
to 2.
I came from 1. So it's like, there's a debate, right? It's been an issue, right? So did Columbus really discover America? No, Columbus didn't discover America because there are people here before Columbus, right? So who discovered 2? It wasn't 4. 1 discovered 2. You understand? So when we discover 2 again, that's not called a tree edge. Call that a back edge because it's going from something to was already discovered. Not only was it discovered before, it was discovered on the way to me, right? On the way to discovering 4, we discovered 2 already. So we're going back to our ancestor. You see that? A back edge goes back to its ancestor. That's why it's called a back edge. All right, take a look at the forward edge now, the green edge, right? That's also 8 was discovered before, but this is different. It was discovered from the ancestor. So this edge is going from an ancestor to a descendant. This edge is going from the descendant back to the ancestor. Everyone see the difference? I'm going to repeat that. The blue edge, the back edge, is going from a descendant back to the ancestor. And the forward edge is going forward from the ancestor to the descendant. And then we have a cross edge, okay? Cross edge is going, it's like between cousins. What's the question, Cheng? Why not go back to 1? From where?
From 4 to 1, because
From
you
4 to 1,
said,
because we don't have a 4 to 1 edge. All these edges are edges from the graph. The question is just what color we paint them, right?
oh, so it's just the idea.
We're taking the edges that are in the graph and we're classifying them into one of 4 categories.
Oh, okay.
So the original graph just had, plain old arrows, and we're color coding them. And we're saying, okay, the dark blue ones mean something, and we're going to make certain ones light blue, certain ones red, certain ones green, depending on how they work. So on this previous slide here, I relate what we just did to the discovery times and the vertex times, right? So it's saying something's going to be a tree edge if it was discovered before the other one, but the other one was finished before the other one. That's called the tree edge, okay? A forward edge is also discovery less than the discovery one was before the discovery other and the finish of the one, but it's not a tree edge. The forward edge and the tree edge have the same, property of discovery, but first we check if it's a tree edge. A back edge is different, right? In the back edge, the DU is greater. It was discovered after the DV, but it was finished before the FV. And then a cross edge, look at the cross edge. We finished the V before we even discover the other one. Okay, so that's the relationship between the classification of the edges and these discovery and finish times. Now, why is this useful? Okay, it sounds cool, we can classify them, but is there a purpose to it? And there are a bunch of purposes to it. One of the purposes is to determine if we have a cycle in a graph. Okay, so why is it important to know if we have a cycle in a graph?
Because simple graphs cannot have cycles.
Well, I think so. It's a regular graph should not have a loop. A loop is going from a vertex to itself, but a cycle means I go from A to B and B to C and C to D and D back to A. That's an example of a cycle, right? So why is it? Let me give you an example, okay? Let's say, as I mentioned before, the department has a graph of the courses you should take in order. Right, so you have to take discrete structures before you have to take discrete math before you take discrete structures. You have to take discrete structures before you take analysis of algorithms. You have to take data structures before you take analysis of algorithms. So we have it's a graph, right? It's a graph. Okay, why would it be a bad idea to have a cycle in that graph? What would that mean?
You end up taking the previous courses.
So let's just, right, that would mean I can't take analysis of algorithms. Here's an actual conversation that came up. So before Dr. Reba was the chair of the department, it was Dr. Zhang. So Dr. Zhang spoke to me one day and he said, listen, some of the other professors who teach software engineering, they want to make your course, CS355, the Internet Web Technology, is a prerequisite for software engineering because I think they would benefit from learning something about, Internet Web Technologies first. So I said, oh, that's funny. Funny that you say that because I think that the people who take software engineering before they take my course, they're in a better position because they understand how to design a software product and different methodologies, and they are better equipped to do the projects that we have in our course. So imagine if the requirements worked as follows. There's a edge that goes from 355. What's software engineering? What's its number?
370.
370. So there's an edge that goes from 355 to 370. It's a prerequisite. And there's a prerequisite that goes from an edge that goes from 370 to 355. So what do you do if you want to register? Well, you can't register for 370 because you didn't take 355. And you can't register for 355 because you didn't take 370. So what do you do? So we want to, in many scenarios, we want to be sure we don't have a cycle in the graph because that could be a problem. So how do we figure that out? So one way to figure that out is we check if they're back edges, right? We run our DFS and we look at the discovery times, and then we we have a back edge, right? We have a back edge. Okay, so here's an interesting thing that in an undirected graph, okay, so like a symmetric graph, right, where every edge, if I can go from A to B, I can go from B to A. I can determine if there's a cycle even faster. Okay, this is sort of cool. I perform a DFS, or I start to perform a DFS, and once I get up to more than V minus I edges, I have a cycle. Why? So everyone know what a tree is in computer science? How many edges are in a tree? So if a tree has V vertices, how many edges?
V minus 1.
V minus 1, correct. Okay, so remember an important thing about trees. Trees do not have cycles. Trees do not have cycles, okay? They are connected. If you add any edge, you get a cycle. If you remove any edge, you disconnect the graph. Trees do not have cycles. So once we reach V edges, we know we have a cycle. Not true for directed graph, because in directed graph, just because I can go one way doesn't mean I can go the other way. So that's a cool thing. I can stop early. Once I know I have V edges, I have a cycle. By the way, if someone tells me how many edges are in the graph, then I don't even need to do the DFS, right? I can just say, oh, check the count on the number of edges. If I know what the count is, then I do that. All right.
Wait, what if the graph is like one line, like connected one by another? Does that also have a cycle?
So you're saying if I have a graph that looks like this with two vertices and one edge,
Yeah.
is that what you're talking about?
Yeah, like A, B, C, D, like in one
Oh,
line.
like that? Well, if I have A, B, C, is it directed or undirected? Like that?
All right, undirected, I guess.
That's not a cycle, right? I can go from A to B and B to C and C to D, but I can't go from D to A,
Mm,
right? Yeah?
yeah.
Okay.
Yeah, but in that case, if the number exceeds B minus 1, it's gonna be like to C. How is that gonna
Well,
have
it
a
means
cycle?
it means that if there's another edge, so it's got to be between two vertices that already have an edge. So it might be between A and B, A and C, and A and D. It might be between
Oh,
B and
okay, I
D,
see.
right? Or it might be between C and A. Understand?
Yeah, I got it.
All right, good. All right, so trees. All right, so a tree also has vertices and edges. As we just said, the number of edges in the tree is V minus 1. Okay, it needs to be connected. Removing any edge from a tree disconnects the tree. Adding any edge to the tree creates a cycle. Okay, our next algorithm is something called topological sort. What is topological sort? It's a way of taking a graph structure and flattening it. Okay, let's go back to our example from the department website. Okay, this is old. Okay, I believe this picture is old. because now 355 is considered an elective, so it's not, okay. But with that, okay, let's say a person decides they're going to take one course a semester. Okay, it's going to take them a long time to finish college. They're going to take one course per semester. What order should they take the courses in? So how do you flatten a graph like this? That's what a topological sort is. It says take something that is, you know, hierarchical in nature and let's flatten it out into a simple, like linked list kind of structure. So how do we do that? All right, it lists these items in sequential order. For example, what course do you take each semester? Okay, so it assumes it's acyclic, because if it's acyclic, it doesn't make sense. Now we have a cycle. Remember the example I just gave with 355 and 370, if they would have changed that requirement, right? So what do? Is we can do a little trick with our DFS. Say as the vertices are finished, we add them to a stack, and then we output the vertices in reverse finish order. What does that mean? It means the thing that's finished last is going to go first in your topological order. So remember, if this is your tree, it's actually not a tree, it's a graph. So the things that are highest up in the tree, like these math courses, these introductory computer science courses, they're going to finish last, and therefore they're going to be first in the topological sort, which makes sense, right? We need to take these courses before we can take these courses, all right? So that's the topological sort. All right, our next topic here is something called a spanning tree. So we just talked about a tree. What is a spanning tree? So a spanning tree means that anything that is connected will be reflected in the tree. Okay, so let me give you an example. So let's say we have a bunch of computers in the room. Let's say there's no wireless access, okay? So in order for computers to communicate, we actually need a wire running between the computers. Now, the wire doesn't have to be running directly, right? So I can have a wire running from A to B and from B to C, and as long as the computers are running a certain like networking kind of software, so they can connect that way. So the question is, you know, which edges do I need to ensure that everything is connected to each other? Call that a spanning tree, right? So let's take an example here, right? So let's say I have A, B, C, and D. But I also, in the same graph, I also have an A to C, and I also have an A to D. So how many edges do I have in that case? And maybe for that matter, I also have B to D. So how many edges do I have in total?
6.
6. Okay, do I need 6 to provide connectivity between all the vertices, the nodes in that graph? No, just this first thing, the A, B, C, D was enough, because I can go if I need to from A to B and B to C and C to D. So we call that a spanning tree. A spanning tree says, give me the minimum edges that are necessary in order to ensure that I have the connectivity. Now, if the graph is not connected to begin with, I can't get a spanning tree because it's not a tree to begin with. It's not connected. But if we have a graph that is connected, so that's the given here. Given a connected undirected graph, right? It's the spanning tree. So what does that mean? It means all the edges have to be part of the original edges, all the vertices have to be part of the original vertices, and there is a connectivity there. Right, now we can go one step further and we can say, okay, let's say there are many spanning trees. It's definitely possible here, right? Take a simple example of a box. You know, a square, okay? So how many edges are in the square? How many vertices are in the square?
4.
4. And how many edges are in the square?
4.
4. Now I can remove any one of those edges and I will have a spanning tree, right? So which one should I remove? So if they all have the same weight, it doesn't matter. But what happens if some of them are more expensive than others? I'm better off removing the expensive ones, because why should I have an expensive route and I can have a cheaper one, right? Let's say one of them has a toll and one of them doesn't have a toll. All right, so that's a important problem, and we're going to learn at least 2 algorithms that solve that. But before we do that, we're going to look at another problem here. It's called the bipartite graph problem. All right, what is a bipartite graph? A bipartite graph is where I can divide my vertices into 2 groups. All right, and all the edges are between the groups and not within a group. Okay. So that's what we mean by bipartite. Bipartite means I divided my edges. So take a look at this picture here. All right. Does anyone see any edges between red and red? No. Does anyone see any edges between blue and blue?
No.
No. All the edges are between reds and blues. All right. So we call that bipartite. Bipartite, right? Because what does apartite mean? It means it's a part. Bi means 2 parts. So we have 2 parts, call that a bipartite graph. Now this graph is more interesting because it's a complete bipartite graph. What do I mean by that? And it's denoted K for complete. M by N, in this case, M is 3 and N is 5, or M is 5 and N is 3. All right. What does that mean? It means every edge in the one set is adjacent to every edge in the other set. You see that? So how many edges does each red one have? What's its neighbors? Its degree? 3.
2.
Why 3? Because there are 3 blues, 3 in the other set. What's the degree of each blue?
5.
5. Okay. So that's what we mean by a complete bipartite graph. All right. So one of the things that's interesting is something called planarity testing. Can you draw it in the plane? And there's a theorem called Kuratowski's theorem. Kuratowski's theorem says that if it has a complete graph of 5, or it has the 3 by 3 in it, or something that is comparable to those, then it can't be done in the plane. So here's an interesting algorithm we can use to determine if something is bipartite. And what you do is you use a DFS or BFS, they both work, and we start visiting vertices. And every time we visit a vertex, we color it. Okay, we have 2 colors, red and blue, let's say. So we color something red, we visit a vertex, we color it blue. We visit a vertex, we color it red. Visit a vertex, color it blue. If at any point we can't color a vertex because it's already, we want to color it red, which is the opposite, but it's already adjacent to something else that's red, then we have a problem. Okay, so that's this last bullet here. So second last bullet. If you try to color neighbor 1 color, but it was previously colored another color, then it's not bipartite. Why? Because that means it's adjacent to a red and it's adjacent to a blue. It can't be, it's got to belong to one set or another. So if it's adjacent to a blue, it needs to be in the red camp. But if it's adjacent to a red, it needs to be in the blue camp. That's a problem. So it can't be bipartite. So we can determine if a graph is bipartite using a variation of DFS, and that can be done in V+E. And it looks like that's it for my slides today. All right, so I'm going to stop the lecture here. Does anyone have any questions either about the material, about an assignment? We haven't spoken about the exam. Should I talk about the exam? So we have a final in class on Thursday, August 11th. What I anticipate happening is we're going to break it into 2 parts. So that if someone wants to go to the bathroom, someone wants to get something to eat or drink, so have a few minutes break in between, and the exam will be okay. So it'll be in 2 parts. It'll be on paper in the science building. So you got to figure out your access to campus, and it'll be a bunch of questions. So I'm going to try to. There'll be 1 question on recurrence equations. So make sure you do recurrence equations. Some students have been apparently looking at the examples, so that's good. You should. I have several of them with worked out solutions. So try to understand what's going on there. We walked through one of them in class together, but you definitely want to understand how to do recurrence. Okay, I'm not going to throw a curveball at you, but the basic divide and conquer recurrence you should be familiar with. But then there'll be other questions where I'm not testing you on the nitty gritty so much. I'm testing you on, are you conversant in analysis of algorithms? Okay, so do you, there'll be questions that are testing whether you've done your assignments in earnest. Do you understand the structure of empirical performance? Do you understand examples of dynamic programming, examples of randomization, examples of this, right? So are you conversant? If someone, interviewed you and they said, oh, well, you took analysis of algorithms during the summer, they start talking to you about analysis of algorithms, they're probably not going to ask you, what is the time complexity of the minimum spanning tree algorithm if I use prim with an adjacency list? So I'm less focused on, little details like that, and more, do you understand how, different strategies are used, the advantage of data structures in different contexts, things like that. All right. So I envision now, I'm not promising, I envision, again, they're going to be 2 parts. You'll hand in one, you can go to the bathroom, then you take the other, and it'll be just under 2 hours because you'll want the time, but I have a class after that, I'll have an exam after that, and other students have other courses. So we'll go to near 12 o'clock, but just, we will have to stop by 12 o'clock. And I envision probably 4 problems in each section, approximately 4 problems in each section, right? So that's sort of it. Anyone have any questions for me?
I have a question, Professor.
Yes.
So this is regarding to assignment 4.
Assignment 4 is the one where you have a choice, right, between the hash tables and the trees. Yeah.
For the whole the main function,
Yeah.
on Tuesday we didn't finish the structure. Like, what is the structure for?
So there are 2 pieces, right? One is building the data structure, and one is so searching for things in the data structure.
Okay.
So you need to have those 4 data structures in order to search them. So we're basically trying to build a list of the structures.
Okay.
And then you can iterate over them. So the advantage of having it in a list as opposed to just having separate items is then you can loop over them just like we looped over different searches. So you can loop over the different types, but also the different structures. So once you build them, you put them in, they're in a list. That's all we're doing. What I don't want to see is 10 lines of code for this data structure, and then the same 10 lines of code for the next data structure, right? So we want to be able to reuse the timing. We want to be able to use, adding it to the, the tracker, right? All that stuff that is common to each of them. So how you do, or which one are we talking about? We're talking the tree or the hash?
Hash.
Okay, so let's say you're doing the hash. So obviously the specific implementation of the hash is going to be different, right? Quadratic probing and double hashing are different than a cuckoo hash. So there's a certain amount that's going to be different for each one. But the stuff that's the same should be once for all 4. So again, first you need to build them. We want to time the building of the structures, and then we want to, do the repeated search in each one.
Okay.
You sound hesitant. Maybe ask a follow-up question.
Yeah. So like what we did at the end of class, structure is just like it's supposed to be built.
Call it what you want. Call it what you want. Okay.
I just call it.
You're building 4 data structures, right? You get that?
Are they all individual loops? So like.
So forget that question for a second, right? You understand you're building 4 data structures. right? You have 4 data structures. So what, if we didn't do assignment 1 together, what most people would do is they'd say, okay, I'm going to write 100 lines of code to test, a hash table of chaining. And I'm going to write another and find out how long it takes and to do trials of different sizes. And then I'm going to write 90 lines of code to do a hash table with a quadratic probing. And we're going to write 85 lines of code to do a hash table with the double hash, and then another 110 lines of code to do the cuckoo hash. And I'm going to take all that, I'm going to print it out on the bottom and let the professor sort through my output, right? So the reason we did that first assignment is to show you how you can streamline it. You can do a lot of different sorts or a lot of different searches and, get it into a nice table. And that infrastructure is only like a few lines of code, maybe like 15 lines of code, and that can be reused for all the different sorting algorithms. So I'm saying do the same thing here, right? Create an infrastructure so that I'm reusing the same code for the timing and the running to call each of the 4 data structures to build it, and then to call each of the 4 data structures to test the searching.
Okay, thank you.
And then put it into a nice table instead of, sorting through. I don't want to see people, I don't want to have to sort through, people writing print statements all over the place. Organize it into a nice data structure. I shouldn't use the word data structure. Organize it in a nice table. The Pandas data frame works. If you like table text, we'll organize it nicely. And that's what we want to see at the end.
Professor, we build our framework based on assignment 3 last time. So one question is when we do the for loop for build and build function and for search and search function, last time you asked me to do for I in length of search function list. I'm not sure why you do that instead of just do search and search functions.
Okay, I think I understand your question. So when you do a for loop, if you're programming in Java, so generally, and not always, but generally, and you do a for loop in Java, we just say for I in the size of something. Well, we don't say for. We do I less than or equal to, right? In Python, what they encourage you to do is to just iterate over the items directly. Okay. But sometimes we actually need the number for something else. So if you look in the plotting algorithm, right, the plot time function, so there we actually needed that number. So, so you have to look, it depends on the context, but you have to, sometimes it's just okay to just use the items, but sometimes we need that number to reference something else, and then we're better off doing for I in range length of whatever, and then we can get the item separately.
Okay, got it. So
okay.
So
it depends on what you're trying to do. They're both valid, but it depends on what you
I can use a counter inside to represent the I.
You can do counter inside, or you can do the counter in the for loop, and then you get the item that you need out of that. You could say item equals list of I.
All right, got it.
Okay. Right. Any other questions?
Professor, you didn't give the attendance code.
I thought I gave it, but I can give it again. It is 0722.
Can I ask something about 355?
Sure.
Yeah, because I just discovered that's the reason why the navigator doesn't work is spelled it wrong, but actually it worked, but it still says outdated, but it's actually working. But for the geolocation one, I'm not too sure how to use it. Even though I look at the document,
yeah,
you cannot just directly use geolocation dot latitude or altitude.
It doesn't,
but
it's not letting you do that?
yeah, I'd have to like
Well, what
use
is the,
some.
like, if you Google it, what is it?
He asked me to do like get current position or watch position. Those are two functions you can't get from geolocations.
Uh-huh. Where did you find it? In the W3 schools or somewhere else?
It's MDN Web Docs.
Here, let me, let's just, okay, hold on, let me share my screen. Am I still sharing my screen?
No.
Let me share my screen. And let's just see if we see something simple. If we do, we'll keep it. If not, we'll get rid of the requirement. Okay, it's not really that important in our, and
And also I found like sometimes even you code something wrong in the JavaScript or HTML, it still work. That's kind of really hard to debug.
it works if it's wrong.
Yeah, like even though you spelled it wrong or you add extra tag, it still work. I don't know why.
Okay, so look at this code. Did you tried this?
Show position and parameter. Let me try to do it right now.
Okay, so go. This is the URL. Oh, so if you put this, so first of all, you need a ID.
Need ID for the. No, I already know how to do the updated thing. I'm just like kind of hard having problem with the APIs. So it says navigator. Your
So you need to look at the example here.
yeah. Seems like it says get current position, show position. Parameters. Oh, I kind of see because like it says you have to use that function, then you probably get the coordinate storing the position. Is that how it's working?
It's a little, it's a little backhanded the way it works.
Okay, so you have to
You're
run the function
passing the
first.
show position to the get current position. So it's not, it's sort of a funny way.
If that's a function, then after you run that function, it seems like you will get the latitude.
Okay,
and the
so what does
position
show
for-
position do?
I don't know.
Well,
Wait.
look at what show position does, right?
Oh,
Okay, it's changing the HTML using a syntax that we're familiar with, right? So X is an element.
yes. X nerd. Oh,
So I would just try putting, put this code in, just make sure you have, the only thing you need that we don't, is you have to make sure you have a element called demo. So don't call it demo, call it, ID
all right. I will try the
for
code.
geolocation, right?
Mhm. Yeah. The most important thing I just want to tell you, I told you the navigator didn't work, but it still worked.
Okay, so I'm not going to erase that requirement.
Yeah,
Okay,
all
well,
right.
I'm glad. Yeah, and I appreciate your, clarifying.
Right. All right. Thank you, Professor.
All righty, take care.
Have a good weekend.
Good weekend, good weekend. Bye-bye.